Let's integrate 3 over x squared minus 4 dx. So I'm going to solve this using partial fraction decomposition, but you could integrate this however way you would like. So I'm going to start by factoring out the denominator, so I end up with 3x minus 2, x plus 2 times x minus 2 dx, and then I can apply partial fraction decomposition. So I'm going to write this in a way that I have two fractions that when I add them together give me what I originally have. So I'm going to write a over x plus 2 plus b over x minus 2 dx. And I don't know the constants yet and that's what I'm going to try to find, because this is how we decompose fractions. So to find a and b, I'm going to combine these two fractions by finding the common denominator between the two. So just not even looking at the integral, just looking at these two terms. The common denominator between the two would give me a x minus 2 plus b x plus 2 all over x plus 2 times x minus 2. And I don't really care about the denominator, so I'm mainly looking at the numerator to find a and b. So I'm just going to fully ignore the denominator and set my numerator equal to my original numerator, which is 3. And now I'm going to solve this like as a system of equations. So actually before that, I'm going to distribute my a and b. I think that makes things simpler, but again, you do what you think is easiest for you. So I'm going to end up having this. And now I can create my system of equations. What I like to do is look at the terms with the same degree on the left-hand side and then equate them to the same degree on the right-hand side. So first, looking at my degree of 1, which is ax and bx, those are my only terms with a degree of 1. And on my right-hand side, I don't have anything with a degree of 1. So I'm just going to set those equal to 0. And I'm factoring out that x and omitting it in my equations, all equal to 0. And then my second one, I'm looking at my degrees of 0, so minus 2a and 2b and 3, and setting all of those equal to each other. And now you could solve the system of equations however way you prefer. For me, I think it's easiest to apply substitution in this case, because your first equation just gives you that a is equal to minus b, and you could just substitute that into the second equation. So it gives you, so if I substitute minus b in for a, I get 2b plus 2b is equal to 3, so that I find that b is equal to 3 over 4, right? Because 2b plus 2b is equal to 4, divide by 4, b is equal to 3 over 4. And I know that a is the negative version of b, so a is going to be equal to negative 3 over 4. And that's it. We found our a and b, and now all we have to do is substitute them back into my integral over here and integrate. That's it. So my integral now looks like this, minus 3 over 4 over x plus 2 plus 3 over 4 over x minus 2 dx. And now this is way easier to integrate. And just for the sake of clarity, I'm going to split these up into two integrals. I think that makes things even easier. And at the same time, I'm going to factor out my constants, so that 3 over 4 and minus 3 over 4 out of the integral. So I have my first integral would be minus 3 over 4 times times the integral of 1 over x plus 2 plus 3 over 4 times the integral of 1 over dx. Feels like I've sinned. X minus 2 dx. And now this just boils down to a very simple u substitution problem. So u is equal to, for this first one, u is equal to x plus 2. And then for the second one, I'm going to choose another variable, v. I did not need to think about that for that long, but anyways, x minus 2. So du is going to be equal to dx, and then dv similarly is going to be equal to dx. And now this looks like minus 3 over 4 integral 1 over u du plus 3 over 4 integral 1 over v dv. And now both of these are going to be equal to log of the inner function of u and v, so I'm immediately just going to substitute that back in. So minus 3 over 4 is equal to the log of u, which we defined as x plus 2, plus 3 over 4 ln v, which we defined as x minus 2, plus my arbitrary constant c, and that is the solution for my original integral.